Hello and welcome. I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to our webinar, New Paradigms and New Opportunities in Distributed Fiber Sensing. And as our presenter, we're very privileged to have really one of the thought leaders in this entire arena. Chris Minto is the Engineering Director of Kinetic company OptaSense, and we in FOSA know him for his stellar work as our first chairman of our technology committee, which produced a substantial body of work that has done a lot to advance the technology. But Chris, we're very interested in learning more to find out what's in the future. So Chris, we look forward to hearing from you.
Thank you very much, Mark. Thank you for the kind words and the introduction. Good morning, everybody, or good afternoon, good evening, wherever you may be in the world. First, a thank you from me for giving up some of your day to come and have a listen to our webinar. Very grateful for all of you who do attend. I've given myself a very grandiose title here, which seemed a very good idea back in January. Because in January I could look ahead to a new world that was all going to be planned out and carefree, and then lo and behold that everything has changed. So what I am though going to focus on is new paradigms and new opportunities. I think having been in fiber sensing for 10-15 years now, an awful lot has changed. There's a lot of conversion in the business. There's a lot of new ideas and approaches out there. I see a lot coming together, and for us at OptaSense, this is our focus, this is our life. I see a lot of new capability being generated at the moment. And so what I want to do is talk a little bit about some of these fundamentals of the technology and what they're offering us, and have a look at some new capabilities and what it may be able to offer you as the client base. So here's what I'm going to talk about. We practice a particular blend of fiber optic sensing based on Rayleigh backscatter. There is going to be a little bit of science, I'll warn you now, but it's only for the first few slides. But we're going to come into that and look at what it's traditionally known for and some things that it's not traditionally known for. It's quite an exciting time, as I say, as the boundaries to other sensing schemes are becoming a little bit blurred. Again, another little bit of science and tech here, quantitative versus intensity. These buzzwords have been sort of bubbling around. They're a bit well known in the downhole oil and gas industry, a little less known in the linear assets monitoring world. I'm going to explain a little bit about the difference between these two classes and what it can offer. And then here's another new paradigm area. For the last 10 years, it's all been about the interrogator. Mine's bigger, better, shinier, brighter lasers. I can go further. I've got more sensitivity. And a lot of that has been fighting against the physics that glass offers. We'll look at that, explore that a little bit, and talk about some of the new glasses that are now coming to the fore, where the glass manufacturing companies are really taking a focus on the benefits of fiber optic sensing and looking to try and help us. So that's a very exciting time, not just the glass, but also what the structure of the cable can do as well. We do a lot of work on that at OptaSense, and it too offers a lot of benefit. So if that's not enough paradigms for the day, I think I don't know what is. So we're going to have a look at those three areas, and we'll look at how they come together with some examples of some of the work we've been doing at OptaSense. So without further ado, let's get into it. So a very quick slide just on OptaSense. For those of you who don't know, we're a vertically integrated fiber optic sensing company. We operate at all levels of fiber optic sensing, from the laser. We own Real Lasers working out of Santa Clara in California, who manufacture the solid state narrow line width lasers, low phase noise, that are used for our interrogators. We work in cables, as I mentioned. We'll deliver data to those who need it, but generally we go a little bit further, and it's all about the information content. The Earth's nervous system, you may have heard us refer to in the past. We've got architectures for spanning nation-sized deployments of fiber optic sensing. And we're at the forefront of working in the latest seismic approaches as well. So we cover all levels. We've got all capability available in-house. So where I'm going to start is the science part. So please stay focused. I've tried to get that in at the beginning. We'll look at the different approaches of fiber optic sensing. We'll look at what they can bring, and we'll shine a light on some newer thoughts. So this you've probably seen before, or a version of this from myself or others within FOSA. The very basics of fiber optic sensing. What we do is we fire a short pulse of light down a fiber, and we look at the light that comes back to us, reflected off the glass itself, a backscatter process. And there's a lot going on in that, and we'll look about it in the next couple of slides. But the basics for most systems out there are very, very similar. And for us, with fiber optic sensing, we fire this pulse of light down the fiber, which will be our blue pulse. There we go, there it goes. A short pulse of light going down the fiber, trying to illuminate a small section at each point. And we look at this long tail of what's scattered back to us. And I'm going to look at what's in that tail in a minute. For us, in the acoustic world, we can place some noise, some source, some vibration. It could be just the environment at any location, and it will modify this backscatter trace essentially, and we can use that to produce acoustic data. And a lot of you will be very familiar with that. There's no new paradigms there. So here's the basics. This is the physics slide. Our launch pulse of light, so a lot of energy launched into the fiber, tiny amount of energy comes back. For years and years of fiber optic sensing, most of this has been the contribution of what comes to attenuation loss in the fiber. And there are three processes really that take place. There is our Rayleigh backscatter, there's Brio-1 and Raman. So Raman was perhaps the first technique to be exploited in sensing purposes. The x-axis here is wavelength, and so from a launched pulse with one wavelength, there is this peak of backscattered energy at a different wavelength. It's caused by the light pulse interacting with thermal molecular variations in the fiber. So essentially, it's a temperature-controlled process that will cause this peak to go up and down depending on what the temperature is. Great techniques, and they allow you to profile temperature along the fiber. Then along came Brio-1, which is a vibrational interaction with light rather than necessarily a thermal interaction with the light. Again, it's an inelastic process. It gives you a peak at a specific frequency, and that peak will move around depending on the extent of the interaction. It's affected by both strain and temperature this time. Again, nice averaging technology gives you the profile of strain or the profile of temperature. But essentially at heart, it's a compound measurement. It's a profile of both, but if you want to separate them out, you can do so with some clever cable design. So DAS is an elastic process. The color of the light doesn't change in the backscatter. And typically, it's been used to be chopped very fast. It's a dynamic process rather than an averaging process. And it's most commonly known for acoustics, distributed acoustic sensing. Dead easy. What I'm interested in today is what happens when your acoustics stop moving, what happens down at our very lowest frequencies. And what we'll see is that this process is not only affected by acoustics, it's also affected by strain and temperature. How can we pull these measurements out from this backscatter process is one of the things we wish to look at in today's talk. This is a pictorial representation of what our DAS data looks like. There's no such thing really as plotting an averaged acoustic intensity over time. And what does that mean? You can't average out the recording of a microphone. Instead, we've got a very rich field of data that's open to us with an additional dimension indeed as well. So here's typically what we might look at. We've got different channels. So this is running along our fiber. So maybe 50,000 channels covering 50 kilometers, vast amounts of data. We'll look at it over time, but because it's a dynamic process, we'll be updating this in real time. And in the background here is my sort of flat perspective of what we may look at. This is typically our acoustic waterfall. And we'll get that by deciding a frequency range to do this sort of live averaging process. Essentially, we can sum our acoustic energy in the frequency range that we've selected and color code it, because I'm running out of axes to be able to plot intensity here. But what that comes from will be this spectral information. So here I'm looking up into the z-axis to my other information that's available. And depending on the slice that I want in the background to visualize, I can just put my spectrogram up and down. Typically, we look in acoustic regimes at maybe 20 to 200 hertz. What's going on outside that? So let's have a look. So here's looking now at a single channel, just plotting it over time running vertically. Apologies for the switches in axes. It's just a little bit easier to visualize. And what I'm looking at is what information can be available to us from the very highest frequency over here on the right down to the very lowest frequencies over here on the left, effectively pseudo-static information. What we do is we will start off out in the ultrasonic. That is, the low ultrasonic is accessible to DAS instruments, the tens of kilohertz. We'll come down through the sonic regime, the sort of 100 to 10 kilohertz. We're then down into the subsonic, the infrasonic, where there's some really interesting stuff goes on. And then below infrasonic, well, what does that mean? There we're into dynamic strain, we're into seismic type activities. And then let's carry on further down below the sort of dynamic changes, and remembering that temperature and strain are going to be coupled for us. It may be rapid thermal changes as well. And then as we get slower and slower to the many thousands of cycles now, rather than thousands of hertz, effectively trending towards DC, we'll find static temperature and strain. That's if your interrogator unit is coupled to DC, coupled to 0 hertz, essentially. And what we find that is then accessible to us is in these higher regions, we've got human activity, we've got environmental noise, wind, and these systems have been highly exploited for all of those areas. So I'm not going to really dwell on that today, but it's very well known and there's loads of content on the internet about that. Moving down through the seismic into the teleseismic, again, reasonably well known for sort of earthquake analysis, seismic profiling, etc. A little bit less known as you turn that frequency knob even further down and start to look at temperature and strain effects. And that's what we're first going to look at today. So if I was to consider the same graph as I had before, forget about looking at the acoustic data, trend this right down now to the low frequencies, what we'd find on our channel and time axis is I can now give myself a z-axis because I've got rid of frequency and I'm just plotting the output of the system itself. I find I'm going to have a composite of strain and temperature. In a single fiber of a single construction, I can't really separate the two. I can't know whether strain or temperature is causing the signal that I'm going to measure. But I can separate them out through some cleverness, and that's where we're going to go and take a look at. So before I do that, I've got to continue with the last few slides of the deeply technical stuff. What I'm trying to explain here in the next few slides, I've got a pictorial representation, is the difference between the two common classes of Rayleigh-based backscatter systems. You might have heard of intensity-based DAS. That's quite commonly used in the linear assets monitoring world, looking at pipelines, looking at leak detection. And you might have heard of quantitative DAS, probably most commonly associated with downhole oil and gas. The two are now converging, so they deserve a little bit of an explanation. So back to our fiber, sending our pulse of light down the fiber, looking at the backscatter coming back. Strain, temperature, and acoustics all coupled in this quite small section of fiber, maybe a few meters long. Here's my pulse going down the fiber. Now, in an intensity-only DAS, what is it that's creating our signal? If we just look at the intensity of the backscatter signal, we've got an OTDR, and that's pretty common, optical time domain reflectometry, a tool that all the telecoms guys use to look at the losses in their fiber. And work out how long it is. Simple stuff, been done for years, no problems with it. Embedded within the signal, though, there is quite a lot more content. And that's what an intensity-based DAS has been pulling out for the last few years. So what we will find is, as that short, coherent pulse is being transmitted out and repeated many thousands of times a second, wherever it is passing, there is a replica of that going back the other way. And essentially, these two are folded over themselves in time, because as the leading edge of it hits my section of fiber that I want to look at, it starts coming back, and then slowly, 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 until finally the trailing edge. So they are convolved into this one bit of space. And what happens when you've got two laser pulses that are coherent being convolved in a single location? Well, let's take a look with an example. So this is an interferometer, essentially. We have interference between the two pulses. And what I'm going to show in the next couple of animations is how that gives us information content we can use. The most famous interferometer is the Michelson-Morley interferometer. It was used in the early parts of the 20th century to show that light actually travels in a vacuum and not the luminiferous ether, which is thought there was a substance that light traveled in. Very clever piece of technology. What it does is you shine a pulse of light down through a semi-silvered mirror, which splits the signal into two. You've then got two proper mirrors, which bounce it straight back again, and the two will meet and interfere in the middle. Here's a little animation that I stole off the web. There's our two pulses of light. They're bouncing off mirrors. They're coming back. My observation point is up here. And if they're in phase, you'll get constructive interference and a bit of a peak. If they're out of phase, they're going to cancel each other out, and you're going to get a dark spot. And if we were to place ourselves at the observation point here, this is kind of what we get. This is an interference pattern. Concentric circles of red and black. So it's a visible laser that we're using here. What the hand here is doing is turning the vernier micrometer down here just to really slightly change the acoustic path length in one of these directions. This one is fixed, changing it to try and force these waves of light to be in phase or out of phase. So you get cancellation or you get growth of the signal. And this is really the key to what it is we're trying to measure. It doesn't give you an absolute measurement of the length, but what it does give you is the path length difference. So in effect, how much this micrometer is moving. So it allows you to make very precise measurements of a change of length, but it doesn't really tell us anything about how long the path length is between the mirrors. So let's have a look at this, what it means for us. So here's what intensity-only DAS does. It gives us, essentially, we've got one measurement, we've got one pulse, we've got one chance of looking at it. It lets us look at this, how this intensity is very closely related to an OTDR. It lets us look very closely at this central pulse, and it lets us look at how it's going up and down with intensity. Now, what you can't tell by looking at this animation is whether your interference is going out, growing, or whether it's coming in, getting smaller. All it tells us is there's change going on. And this is one of the key facets of an intensity-only DAS. It tells us about change, but it can't tell us about direction of change. It can't tell us about magnitude either. This is what a quantitative DAS will do. It gives us this additional piece of information. Here we can see whether the number of fringes are getting smaller, whether they're getting bigger. It can count them as they're going past. And essentially in a quantitative DAS, rather than the measurement that comes out of it just being how bright is the central spot, we're actually giving as our output in radians this difference in path length of the interferometer. So essentially from a fixed transmit pulse, it will tell us how big this illuminated area is changing by. Is it getting bigger or is it getting smaller? It tells us the direction and it tells us the size. So it's a much more precise and fundamental measurement than an intensity DAS. As I said, this has been developed specifically for downhole oil and gas, been used for vertical seismic profiling where you need to know strain, and you need to know the direction of it. It's less been used on long linear asset type jobs. It's been constrained to lengths of maybe about less than 10 kilometers. So this is the sort of information that comes out of both of them. If you just want to color code it, as we were saying, cut the acoustic information, take a look at it, we'll end up with an acoustic picture with channels running horizontally, time in this case running vertically. This is our waterfall process. And here I've taken an example of a train moving. The train will be moving along the fiber, but the visualization of it means it's moving in time as well as space. And so we end up with the speed out of this. An IDAS or QDAS can do both of these. What you'll see is you've got great ability to show where an object is. You can listen to the sound. You can pull out speeds. You can even see that there's content within this that is moving with the train that is related to the train itself. Here you can see where train is pulled up, stopped for a while, accelerated, decelerated, stopped, etc. Great loads of useful content for an IDAS. QDAS will give us something a little bit more. So here's how the two behave. Same picture, just looking at it a little bit more figuratively now. The intensity DAS doesn't really know whether things are getting bigger or louder quite so much. It doesn't tell us about the amount of strain being put into the ground under the train. We've got a great load of acoustic information, but we can't pull out any of the sort of static content. Nothing is in phase with each other from that problem of the interferometer that we looked at earlier. Whereas with the QDAS, we've got the same acoustic content. Everything is beautifully in phase now. Every channel responds to a given input as it should. And here, all I'm doing is figuratively shining down a plane wave down the fiber itself. And so it'll go along at the speed of sound in the fiber. And from this, we can add channels together to give us more gain. Here, there's too much noise. We can't do that. There's no processing gain to be got if nothing is in phase. So it allows us to get a lot more information out of the system. So here's a nice example. I don't know how well the video is going to go for those on the poorer bandwidth connections. Hopefully mine will hold up and the children haven't come home. Here's a couple of videos just showing you what from the same signal, what it looks like in both of these regimes. So here's the intensity only DAS playing. Something's getting louder. Trains going past. We see the signal going up and down, and then things quieten down. It's a bit of a jumbled mess, though. We could see where there were some peaks and troughs in it, but they weren't necessarily coherent. It wasn't going up and down. It wasn't a regular signal. If we then go and play the QDAS version, we can see ka-thunk, 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 ka-thunk as the trucks or the bogies are going past. It's a very regular signal because instead of just measuring the rough noise field, it's measuring the strain on the fiber in absolute units rather than some sort of jumbled intensity units. And we can see that these peaks align with each pair of trucks. So it may look similar on the surface, but underneath it allows you to do an awful lot more. And this is the so what question. You know, it's like, Chris, well, that looks great. I love all that extra information, but what's it going to give me? As I said, this has been used for downhole oil and gas for years, particularly for seismic information. A little bit less accessible in linear assets world because the technology has been limited to around about 10 kilometers. They run out of light after that, and you need new techniques to be able to go further. And they've, in the past, been less successful. So we've been working on this for the last few years to develop a system that will push us out to 50 kilometers. This is our Plexus system. There's some seismic information recorded from a subsea cable, looking at shots, running out to 50,000 channels, getting samples out every meter. And suddenly we can do the downhole job that previously we may have been interested in only in the sort of 10 kilometers in well. We can run that out to much greater distances, more sensitive and integrated with our OS6 monitoring suite for linear assets as well. So what does it buy me? So it allows us to look at the fundamentals. It allows us to look at what is the path length changing in the bit of fiber that I'm illuminating. And this is where the temperature and strain information is, for example. If I've got a measurement where I need to look at what's happening to the fiber at that degree of fidelity, you really need a quantitative system. If you're just after acoustics, you know, a normal footsteps detector, vehicle detectors, and intensity DAS is absolutely great. And we're not stopping with intensity DAS. But if you want to look into that signal, if you want to look at wheel flats running within a train, if you want to try and pick up a rail brake when the train is moving, if you want to look at strain that's sitting slowly going into a pipeline at the same time as doing its acoustics, you're going to need this sort of system. So this is my first paradigm for the day, but I'm not finished on the paradigms. We're going to come back to a little bit more. But this is the opening point. In order to get to greater and greater capability, in order to develop new applications that will sit on top of these basic acoustic applications, which I think in a few years' time we'll look back on as maybe being a great start, but a bit naive, we need to migrate to these quantitative systems. So the glass is really important. Let's come and have a look at the glass. So I mentioned that we've been fighting against the glass for many years, having to try and get to longer ranges while the glass is trying to throw our energy away. There's not been much change in glass over the last 20 years, although I know any of my glass colleagues would argue with me about that, so I'll maybe retract that. One of the biggest things has been moving from a conventional glass to ultra low loss fibers, needed if you want to go and span the Atlantic. And there, conversely for us, the approach has been to try and remove some of that backscatter and try and get the signals to go further, because for a telecoms engineer, it's all about loss between point 1 and point 2. We're interested in the loss, but they want to try and minimize the loss to get their signals further. So for us, that can still be exploited. It's a battle between the amount of backscatter, which shows how much signal is accessible to you, signal to noise ratio, etc., being able to resolve that path length on the interferometer, and how much is being lost against the glass, which controls how far out you can get. So ultra low loss fibers have been a good move for anything that's offshore, for example, in trying to look further down the fiber, because you've got more light for longer. Looking at that approach, though, that's been turned on its head in recent years by the glass manufacturers, and there's been a lot of efforts to change the glass and change this balance of backscatter versus attenuation. And there's a few different approaches. We will probably all be aware of fibre Bragg gratings, which is a different class of distributed acoustic sensing, where with a single wavelength, you're trying to focus on an etched grating in the fibre. A new approach is to put in weak versions of those, designed for a specific wavelength, but to give a little bit more backscatter at a certain point, so we can get a more controlled and precise signal and more of it coming back, which gives us a lower noise floor. So more light coming back to us means lower noise floor, and in many cases it'll also mean more loss. But if our interests in range are not that great, or if we want to put sensing at a particular point down a cable, then any of these approaches are good. So weak fibre Bragg gratings, or high backscatter fibers, where regular gratings might be etched into the fiber randomly and periodically. Microstructured fibers, which are trying to encourage more backscatter sites. It's quite a dynamic area of technology at the moment. It's hugely helping ourselves as a system designer, because we now get more than one tool. Rather than just get a bigger and beefier interrogator, we can look at what the glass has to offer, which helps us approach different problems. And so we've used this in our ODH4, our ODH4 Plus, designed to be exploit the maximum that these newer fibers can offer. Here's an example of what it does before with our normal ODH4 and after with our ODH4 Plus. Normal fiber, high backscatter fiber on the right, you can see it's not increasing the signal, but it's had a dramatic effect on the noise floor. So this has got huge potential, particularly for the shorter range fibers. And we can see the effect of different gauge lengths and being able to pull out information content that just wasn't visible before. So this has got huge potential. It's already been adopted, beginning to be adopted quite well by the oil and gas community. And we hope to see more of it where it's appropriate. So the next thing is the primary cable construction. So we covered glass. So what about the cable? I did say I was going to come back to that. So there's some basic fundamentals of the cable that are really important. How that's constructed has a massive effect on your signal. So let's just compare a really simple case, a tight buffered cable. So this is a glass with a buffer material that's molded into it, stuck in the ground like that, maybe some armor. Compare it to a more loose tube. And here I'm thinking a little bit away from the sort of telecoms loose tubes that are gel filled. We still use them, they're great for acoustics, but let's just think of a fiber slopping around in an empty tube. What we need for acoustics and for strain measurement is really good coupling between the glass, between the cable, between the surroundings. Because we're measuring our signal in the glass, back to our interferometer, the path length difference, that's only in the glass. So it has meaning in the glass and then less and less meaning until you get to the outside world, depending on the level of coupling. And so a tight buffered fiber will have the best coupling possible between the glass and the cable, and then you have to consider how you couple it to your outside world, whether you're just looking at strain in the soil, for example, or you want to look in a pipeline, you might want it glued directly to the pipeline. Whereas the loose tube concept that I have here, an empty loose tube, the fiber has a lot of freedom to move in the tube, which means that it's very poorly coupled to strain. But both of them will be coupled to temperature. And so if we've got a composite signal of strain and temperature, and we've got a composite approach on cables, we can solve two simultaneous equations and then look to separate the two. And that's what we'll get onto as some practical examples in a minute. One important thing to note, not all cables will give the same output. The level of responsivity to temperature and strain will vary somewhat. Strain is a little bit different because we have some standards in terms of what we expect from the glass. But if I was to just plot out, look at the phase change now, the composite signal, this path length difference, which is a sum of the temperature and strain variations, look at that from a single point of my cable in the ground and look at it over different cables, we'll see that I've got a big old temperature variation going on, just the natural environmental variation of temperature. So we'd expect both of them to be responsive to that, maybe not equally though. So these are an absolute temperature reference, my blue and my red, and you can see that buried within that I have got one of my cables that is tracking it beautifully, and a whole lot of other ones that have got an entirely different picture altogether. So you really need to know what's going on with your cable. I'm going to come back to that in our real life example in a minute, but I got one last paradigm buster to bring to you today. And so it grows on this area. So we thought about our cable can be designed to be selective to strain and temperature. Well, why not go a bit better? If you can consider the construction of your cable to have an effect on the glass. So it doesn't just need to have to be strain and temperature. There's a class of materials called magnetostrictives, which are magnetic, strictive for strain. These materials will change length and magnetic field. And then there's a whole range of other types of materials that will be similar. If you can put a magnetostrictive coating onto your glass or embed it in your cable, then what you will find is that a normal piece of glass is unaffected by an electromagnetic field. That's part of the cuteness of the design of fiber optic cables. So if we suddenly wanted to make one that was affected by a magnetic field, we can conceive of a cable using secondary coupling. So the magnetostrictive element is doing its bit, and it's putting a strain onto the fiber, which we can pull out as strain. If we know the level of coupling, we can know what magnetic field would cause that difference. And that will allow us to then open up a whole new range of jobs. And it doesn't have to just be magnetic fields. Whatever you can conceive of that you can pull out a transductive mechanism, a second order transductive mechanism in the cable, will allow you to see something new in your fiber. So here's an example. In this example here is looking at the design of a cable that is intended to be pressure sensitive. Here's the response of hydrostatic pressure to a bare Hytrel coated fiber, so just a normal bit of buffered fiber. It's got a slightly negative response to pressure. As you put the pressure on, the path length difference decreases, you get a negative output of the radiance. The gradient isn't, the sign isn't important, whether it's positive or negative. But here's a cable that we've designed to have an excessive positive response to pressure. And the difference is the size here. If I zoomed in on this, you'd have a lovely linear graph, but it's only varying by about 1/10 of a radian, 2 pi radians, 6 and a bit radians in 360 degrees, that being one set of fringes. So tiny change with 4 bar, 4 atmospheres of pressure. Whereas let's compare that to my, times 10 to the 4. Let's compare that though to my Proteus 606 cable. And here I've got orders of magnitude change in behavior that we can track. And the steps here are just by incrementing that pressure in steps. So 3,000 radians of change compared to 100, 200 radians of change in the opposite direction. So what this means is I've got a cable that's pressure sensitive. And there's some examples there picking up pressure signals in air. Okay, so last section, illustrations of next generation capability. So we talked about strain, we talked about a quantitative system. Let's bring these together to see what we can now do. So taking a fiber, applying a linear strain to it, nothing in acoustic world now, I'm just looking solely down at this very low frequency. I should be measuring the path length difference. So if I double the strain, I should be able to double the number of radians of change that I see. And so here we are, just loading up a section with a piezo stretcher, loading it up with really small amounts of strain, 30 microstrains. Starting at 0, running it up to 120 microstrains, ramping it back down. It's a nice linear response to strain. There's a few other things going on over here off the section at which we're straining. So what is that all about? So I mentioned that strain and temperature were coupled. And so here, if I just take an unstrained part of the cable and just leave that free running in my lab on the bench, I'll see I've got a lot going on here. The signal's varying by an appreciable amount, but I've not strained it anymore. And there's noise on it as well. And this is not random noise. This is all down to temperature variations in the air in the lab. We can measure this and quantify it. And we can quantify the response of the cable. So we talked about our dry loose tube and our tight buffered. Let's have an experimental design now where we run through a Quant-IU with strain monitoring capability. We run it through our tight buffered, which should be responsive to strain and temperature. We run it through the loose tube, which should only be responsible to temperature. We solve our simultaneous equations. I should be able to get both of them coming out. And here's what we get. So green is my temperature measurement at the point in red. This is just taken from buried in a field outside the back of one of our offices. The red curve here is the one we saw earlier from the loose tube that's sensitive to temperature only, beautifully tracking the local environmental temperature. One taken with a platinum resistance thermometer, the other one taken from our DAS reading of the size of this, the gauge length of my interferometer. And then the second cable here, the tight buffered, gives us this blue curve. And you can see it's definitely affected by temperature. We see it, but it's departing from it, and it has extra features. We solve the simultaneous equations. I plot my temperature, I plot my strain, and suddenly I've got a bit of an answer here that I can now pull out my temperature variation. And here I'm only looking at a couple of Kelvin variation in temperature, and my strain variation in red, where I'm down in the sort of single digits of microstrains, really small amounts, 10 to the minus 6 of the length of the cable, of the gauge length, I mean. And here, where these odd things are going on, we haven't done anything to the fiber. This is actually where there was rainfall taking place over the 70 hours of measurement. We had a little bit of rainfall, putting some additional components of signal into the ground. It's getting heavier, it's getting spread out, it's drying out. It's a dynamic environment. But because we've got this exceptional strain sensitivity, we can visualize this not just in one channel, but of course in every channel. And so putting it together into real life, we got all the acoustics going on. We can forget about them, we can use them, we can exploit them and do the normal acoustic job. We can also look at these strain and temperature components. So we'll have our core noise floor. We'll have a daily temperature variation that sits on top of that, maybe 10 Kelvin or so. Sitting on top of that would be an annual temperature variation. Of course, it won't be so much in the soil, maybe only a couple of K a day in the soil, maybe a little bit more over a year. If we then, as a thought process, apply some strain over a year, we'll see those two signals converge together because we're measuring the emergence of them both. By separating them out in cable design, we can pull them back and resolve them individually. And what we see from our cabling is we've got a sensitivity we can measure to temperature, a sensitivity we can measure to strain. We would need to have two cables, as I've shown, in order to resolve the two. But here's the key point. So our sensitivity to strain, 70 radians per microstrain. Well, what does that mean? So a fiber optic strand will fail at about 3%, 30,000 microstrains. So that's massive compared to my 74 radians per microstrain. If I consider my noise floor is down in the milliradians, I've got about 9 orders of magnitude to play with. So I could potentially look at a huge variation of strain or indeed temperature. And here's the thing. If our temperature variation we're only expecting to be this big compared to the strain variation, I might not even need to separate them at all. Here's a quick example of what we've done in real life with this. We've been working with a UK company, Sustainable Pipeline Systems. They've got this really novel approach of making pipelines as you go, make them in the field from polymer feedstock overwrapped with steel wind. You can embed fiber into the wind, and what we've been looking at is pressurizing this and looking at the behavior of the strain. And so there we are running through pressure cycles at about 50 bar, dropping from 40 to 50 bar over 3 or 4 days. And here's a few of my measurement points taken on this winding, and we're just tracking those breathing modes of the pipe, and at the same time plotting out the temperature variation. Of course, we could choose to separate them if we wish. There's our one-to-one registration against the pressure cycles, and there's our behavior as we ramp up the pressure from 0 to 20 bar. Keeping in mind the really small size of strain that we're looking at here, this is down in the microstrains. It affords a new class of measurement for these types of problems. Here's another example, just popping a sandbag onto the pipeline and looking at it on neighboring channels. So where the strain is not being felt by the pipeline, we don't see much of a signal, channel 4 through 4, but in the middle, where in the center of our measurement, where we're a little bit oversampled the way we carried it out, but we can see very clearly the step change in strain as the sandbag is placed on the pipeline. And this is cast against a sliding background because we haven't compensated for temperature in this case. So caveats and comparisons, just for the last couple of minutes. One difference is a Rayleigh-based measurement, you need to observe continuously. Because we're based on how this gauge length is changing, if I go away and I come back, I'm starting at 0 again. I may have recorded my measurements and I may go, oh, this is where it was, but I don't know anything about what happened in between. Whereas with a Brillouin system, you can measure the amount of frequency shift, or the Raman system, the responsivity to temperature, go away, come back, and you can see what's changed. It's a live approach though, it's dynamic, we can do it in real time to the sensitivities we've talked about, and of course we can do all the acoustic work as well. So that has been a bit of a focus on the technology for today's talk, some new ideas that I really wanted to be able to share with you, so thank you for sitting through it. I hope it's been able to get across these concepts of the new paradigms. Here's what I've got to say. DAS can offer a lot more than acoustics. It's a misnomer. It's not DAS, but I think we're kind of stuck with it. Distributed Rayleigh sensing, it doesn't sound that good. Distributed fibre sensing is just too generic. So if somebody's got a good acronym, come either patent it or come and tell me about it. Quantitative DAS, QDAS, this opens the door for us to a much wider range of measurement opportunity than we've had before. Couple that to cable design, and it opens the doors to new types of measurement. Glass with it helps us look at putting the focus where we need it, rather than just suffering what is given to us by the glass of opportunity. So hopefully what I've been able to show you is that we're on the cusp of a whole set of new paradigms here of measurement regimes that are being opened up, making Rayleigh-based backscatter a much more versatile technique, and being able to bring new advantages to industry. So if you want to look at very long ranges, if you want to look at all the normal acoustic things that DAS is known for, and you want to do some new stuff, then the door is opening to be able to do that. So I hope you've enjoyed this talk. I'm going to hand you back to Mark now, and I'd just like to thank you for paying attention.
Well, thank you, Chris. And to ask a question, you can type it in a box and on the right, and I will pass it along to Chris. Chris, I'm kind of curious. I assume you've been working closely with a number of the cable manufacturers. How do you see this? Are you going to need? Are users going to need to retrofit to install new cable, or is this something that when the opportunity presents itself, there'll be an opportunity to upgrade to fiber that is more conducive to some of the application or some of the uses that you're describing?
I think there's a bit of a mix, to be honest, Mark. I think perhaps what I've shown here highlights that when you're putting in a fiber for a greenfield job, you've maybe got a little bit more to think about in terms of what you might want it to do. Whereas in the past, it would have been, pull up the catalog of telecoms fibers, get the cheapest one that meets the spec and puts it in the ground. That's not going to go away. But if you're wanting to think about doing more, and as new capability starts to be announced from myself and from others, it might make you think about what does the actual cable need to do and what capability does it require. So I think that is changing. I think with existing cables, there is a really wide range of capabilities that individual cables can offer you. And I think I had there you go, this one here. This is just a very simple example of looking at the temperature responsivity of the cables. It's very broad, and so you can take cables and you can characterize them, certainly, and then be able to know what it is they can do. But it's a little bit hard to say you can do X with Y. It's easier to plan ahead, but certainly, the door isn't closed to capability on existing brownfield cables.
Okay, so I'm sure that's encouraging, though, to the cable manufacturers, an opportunity to sell new cable. How would you distinguish the EM strain from elastic strain when they act simultaneously on a new fiber with EM coating?
Yeah, so some of that is down to your job design, really. If you're trying to think about EM strain compared to normal elastic strain, some of that is going to be induced by the environment that you're expecting it to be in, of course. And this is one of the points that I was making towards the end here, you know, is if in your environment you're expecting one component to be quite small, such as you're looking for a large elastic strain evolution over time and you don't expect temperature variation to be big, you could potentially just ignore it. And again, with the magnetic strain, elastic strain argument, if you're expecting one to be quite small compared to the other, you could ignore it. However, if you're trying to separate the two out with the maximum capability, you're back to then needing two measurement approaches. So a composite cable or two cables, one responsive to elastic strain, one responsive to elastic and magnetostrictive strain. And then two simultaneous equations again, separate the two things out completely.
So the next question, actually I have a couple of questions sort of related, which is, do you see an extension in the range that's available for DFOS, going longer distance as a result of some of these technologies, obviously using the appropriate cable to be able to do it?
Well, I think that's a hot topic at the moment. That's never got old, is wanting to be able to go further and further, either with conventional designs of IDAS or with QDAS, with or without the benefits of cable. There's a lot of interest in the marketplace in terms of, you know, going further and further ranges. So I'd say, you know, yes to that. Clearly, we're all interested in that because in some situations you're constrained by not being able to put out more than one. If you're looking at a long ocean crossing, for example, you just don't have access. Putting down marinized units has its place in some jobs, but for example, offshore wind farms here in Europe, they're moving out to over 100 kilometers distance offshore. People want to go further, so it's an active area of development for us. Glass helps, but you can't always control what glass is there. So I'd say that that's still a need for interrogator designers.
So the next is there any work on researching sort of multi-directional strain fiber design?
So that's an interesting one, yeah. So some of this work that we showed here, I didn't bring it up because it was getting into a little bit too much detail and I was already in danger of that, was looking at controlling beam patterns. And you can do quite a lot to control beam patterns of the fiber. One of the great drawbacks of a normal linear fiber optic cable is the response is a great big null in the middle. And so part of the story is moving to, well, we can design that null out. We're doing some work in that area. Another part might be to develop helical cables, which take it out by design. And then they all still tend to have polar symmetry though. So if you want to get into multiple axis ones, you need fibers that will respond in specific directions, and you need to lay them so those directions are laid appropriately with what it is that you want to measure. So that's a tough nut to crack. I think there are tools starting to open, we see in cable design, to help you approach that, but it's quite difficult.
And speaking of tools, another question is about the development of algorithm or analytic tools how shall I say, describe this, to evaluate or to detect phenomena based on the increase in data that you're receiving from this approach.
Yeah, so that's a whole nother topic in itself. I'll book in my next talk on that. But it's an interesting problem. So in our, I mentioned our OS6 platform there, we've taken two approaches to this. We've taken some supervised learning, machine learning approaches. I think they have their area of capability that address some acoustic problems. We've also taken statistical automatic learning approaches that have their approach in other classes of acoustic problem. And I definitely, whoever's called for that is saying the right words. I need to get away from a lot of the human-driven channel by channel approach into using more automated techniques, because as the volume increases, there's less chance for the humans to influence the supervision of the automated detectors, and there's definitely a requirement to try and reduce the setup element, setup cost, and the variabilities that humans introduce into it. So we're a big fan of that.
And the next question, I don't know if this is one of your competitors, but they're interested is, do you foresee some new markets for DFOS opening up as a result of this? I think they're looking for you to tip your hand.
No, so I think let's be generous. So I think if you've got new measurements,
right,
it definitely opens the door to new jobs. If you suddenly can start to measure magnetics, well then great, we can go out and do things that we've not been able to do with DAS before. So it's limited by your imagination as to what sort of jobs need to be done, what do you need to measure, and then this is the part I like best, is it now becomes a systems engineering problem rather than a physics problem as to pulling together the components to be able to tackle it. So the short answer is yes. We're interested in a lot of areas that are well out with our core market. I get encouraged not to pursue all of them all of the time because you need a business at the end of the day, but I see a lot of exciting potential out there in very non-standard areas.
Well, actually, that sounds like a great note to stop on. I will follow up on the question that we always get, which is, of course, this presentation will be available on our YouTube channel. So for folks who want to see it again or see the PowerPoint again, that will be available there. It should be up within, well, usually a day or so, if not shorter than that. So thank you very much, Chris, for a very informative presentation, although I think we'll probably take you up on that follow-on one in 2021, and we'll hear more about some of the applications and some of the evaluation techniques that you'll be using. So that concludes our webinar, and just a reminder before we stop, we will be doing one on October 19th with well, we're still working on the details on that, but we'll have more information about that coming up. Thank you. And it won't be the October 19th, it's November 19th, the next one. Thank you, and that concludes our webinar.
Thank you, Mark. Thank you, everyone.